Welcome back, everybody.
We have returned.
We have a blissfully short video here.
Yeah, you guys have done some marathons at this point.
You've done some marathons. This one is going to be blissfully short because honestly, the best way for you to absorb this information is on your own, going through the slide deck.
Yeah. And
So what we're going to post here as a video is really just a guidepost for how you should look at the information that we presented to you in the slide deck.
yeah,
Because what we're looking at here is this is the what's called the phase diagram.
not to be confused with a phasor diagram,
No.
which is how we deal with vector math. This is a phase diagram. So think different states of matter,
Different mixtures,
different
right?
mixtures, and those types of things.
And so in the metal world, a phase, unlike that, unlike in electricity where it's a vector, it is just a homogeneous structure
Yeah,
within a metallic
within a metallic element.
element or alloy.
Metallic alloy. Thank you.
So what we've got here is on the bottom axis of it, you have the percent carbon, because steel is an alloy of iron and carbon.
Yeah. So carbon is along this axis down here.
So you can see that it's the percent carbon by weight is along the bottom there.
Yeah, right down here. And then we have this, like as we go to the right, the amount of carbon in the alloy is increasing.
Yeah. And then on the y-axis, we have the temperature at which these phases form.
Yeah. So this is we're relating the quantity of carbon in iron and a specific temperature.
Yeah. And you'll notice that, like up at the very top of that, we have a region that is liquid.
Yeah.
So that means that in those percentages of composition, the state is liquid, so it is
Yeah.
it is not in a solid phase.
Yeah. And so like here, and so that basically is topping out at, what is that, 1539
Yep.
C? This graph is in Celsius,
Yeah,
it appears.
yeah, and
So-
and then if you go and look at like that dashed line
Right
in the
here.
middle there, where we have an arrow pointing and saying eutectic, that is a eutectic point. This is an equilibrium that occurs, and basically like because it's a lower melt point at that mixture, it wants to reach that equilibrium when it hits that temperature.
Yeah.
And you'll notice that that is a lot lower. That's at 1100.
Yeah, 1100 C, approximately.
1147, it says on there.
Oh, 1147, yeah, right there.
So when you're looking at this, you like keep in mind that like, these are existing, like these are how the phases organize themselves at different mixtures at different temperatures. What it means for practical terms is if you're elevating something that is a solid steel alloy and you do that in the presence of any carbon, it will absorb that carbon to lower its melt point.
Yeah.
And it's actually a violent kind of like all of a sudden it just starts making a puddle,
Yeah.
blows a hole in the side of things,
Yeah.
sort of like a slagging
Yeah.
hole in the side
Yeah,
of things.
I wonder, I've seen it happen, like in videos, and it's a very sudden reaction. It is not the conditions were made to like make it very apparent what was happening, but like when this happens, like it is a almost instantaneous transition.
Yeah.
Like
And it's scary. Like I've
Yeah.
had applications. At one point, I had a retort furnace which was made up of an Inconel, which is a low carbon steel nickel alloy, so that made up the walls of the furnace,
yeah,
and we were heating it well above that 1147 C, but we were putting in a graphite crucible.
Yeah.
And we were also in that atmosphere. We were running an atmosphere that was reducing, and so it was 80 something percent hydrogen.
Yeah. Okay.
So if you think about like superheating hydrogen, everybody remember the Hindenburg?
Yeah.
Um,
Hydrogen explodes.
hydrogen
FYI.
explodes in the presence of oxygen, but we reduced the oxygen there. But the only thing that was keeping the oxygen out of that superheated hydrogen
Was this crucible?
was the
the
Inconel retort, right?
Yeah.
So we had to paint a ceramic coating on the outside of this crucible, but that like eventually started ablating away, right? And so it was always like we were constantly reapplying it, and it was just a terror.
Yeah.
Because what would happen if we allowed that carbon to come in physical contact with this steel alloy
Yep.
that is above 1147 C? I think we were doing it at about I think 1600 C.
Yeah. Okay.
And
and the like the thing here is like, as long as you're above this like critical temperature,
yeah,
this reaction is nearly instantaneous.
it would just instantly blow a hole in the side of it, leak super hot hydrogen out into our oxygen-rich atmosphere,
Yeah.
and immediately cause, at the very least, like a blowtorch of the hydrogen-oxygen reaction.
Yeah. And if you guys like want an idea of how violent that type of reaction is, look at a space shuttle launch.
Yeah,
Because
that's all that is.
Like that is literally the energy released there, and all of the flames, all of the thrust that is generated, that is literally just from remixing hydrogen and oxygen together.
Yeah.
And like when that happens, a tremendous amount of energy gets released.
So essentially, like the danger there was if that
Yeah.
ceramic coating laid came off of
Failed.
the graphite crucible, we would have instantly blown a hole, which would form a nozzle for a rocket.
Yeah. And then you inject high temperature hydrogen into an oxygen rich environment. For anybody that's unfamiliar, when you inject heat into almost any type of chemical reaction, it speeds that up.
Yep.
So you get like it potentially, there are things that we have to do to materials for all kinds of reasons, that we have to control these environments very readily. And to do it safely, we need to understand like how these properties work together. And so this is also like part of that scenario.
There are consequences to this. It is
Yeah.
not just an in theory or nice chart that we like. You should really spend the time with this, and that's what we want you to do at the end of this video, because like the next little bit of this video, it's going to go fast.
Yeah.
Because we're not going to touch on each of the points that are on each of the slides. What you need to do is you need to relate each of the points that are on the following slides
Yeah.
back to these two diagrams.
Yeah. And so like we kind of got a little bit off topic here when we were talking about giving some examples about like why we care about these
I'm
different
sure
states
they're
of matter.
happy we're talking about explosions.
Yeah.
But
Let's go back and let's define like what we meant by eutectic one more time to just kind of bring everything back.
it's that minimus point where
Yeah.
basically like this is the lowest melt temperature, so it's going to gravitate towards achieving that mixture because it can achieve mixture when it's liquid.
Yeah.
And so that feedback cycle that you get for the eutectic point there is what is happening there. Now notice this happens in like the 60 something percent carbon by weight
Yeah.
region. What this means is that this is not in the steel thing, and
Yeah.
so that's where we get to the graph on the right here. This graph on the right is really just a blow up
Of a very small region
of a very small region over there in the middle left
right here.
of that, and this is what we consider the eutectoid steels,
Yeah.
which is what we all kind of consider as steels as we know them.
Yeah.
So all the various different portions of steels are relatively low carbon when you look at the whole spectrum of carbon mixtures, right?
Yeah.
And anything really to the right,
Right.
of that region is considered, ironically,
Cast iron.
yeah.
And
And that's why we have the word irony. Now that I think about it, like this
Yeah.
just occurred to me. Irony is that iron, like cast iron, as we think about it, is less iron
yeah,
than steel.
is less iron than steel. like in absolute terms, it is less iron.
Yeah, so your cast iron skillet, it's actually got more carbon in it
Yeah,
than a steel
than a steel does.
does.
And there are, I mean, there. Are, the other thing to point out here is that, again, remember that the material properties that we've been discussing, they are neutral. There are times when cast iron is the appropriate material for an application, and
Yeah.
and it outclasses
Cook with it every time.
cook with it every time. But like there is one characteristic of cast iron is that it is because of its behaviors, it's very dimensionally stable compared to steel or lower carbon alloys
Which can expand and contract quite a bit with heat.
with heat. And so like if you're in higher temperature applications, and you don't want whatever it is that you've made,
Or you want that as like that dimensional stability, like for instance on a tool surface.
Yeah.
So like the reason why you prefer a cast iron
Like-
table for like a bandsaw or for
for a
ways-
machine tool or
machine
something.
tool on
Yeah.
on a ways, it's because it's dimensionally stable.
Yeah.
So yeah, again, neutral things, right?
Like application drives whether or not something is a desirable characteristic or an undesirable characteristic.
Yeah. So, for the most part, when you go through these following slides, you're going to really be just referring to this chart on the right here
right-hand
because
side.
that's a zoom in of that region over there on the chart on the left, but it's the one that we're actually talking about. Like
Yeah.
everything in the following slides exists on this.
Inside of this specific chart on the right hand side here.
Yeah.
So when we're correlating stuff, we're coming back to this specific chart.
Yeah. So the expectation of this is that you're going to want to pull up the actual slide deck
Yeah.
that we provide to you on Canvas, and we want you to spend a good amount of time
Yeah.
relating the following slides back to this slide. So let's look at how that looks on just one of these to kind of start off with.
Yeah.
If we go to the next slide, we're going to talk about a particular phase on here, and that's ferrite, which is an interstitial solid with a small amount of carbon dissolved in alpha iron, and it is BCC in nature. So this is a phase that is body-centered cubic. It is the softest structure that appears in the FEC category, right?
Yeah.
So we've got ferrite here, and that's a little of what it looks like there. So you can so what you want to do is you want to take like, okay, I've got 723 degrees C and 20.025%, and then we
So if we
go
go
back
back-
here. Let's relate that to the 725 C.
So we're our temperatures on our y-axis here. So we're somewhere like around.
So you can see the the line at 727 there, right?
yeah.
And a maximum solubility at 0.04, 0.02 we see right there at the beginning of that triangle. So we're basically talking the region around that really slim triangle right there, right there.
Here, like in this area right here.
Yeah,
This is where kind of ferrite is hanging out.
like soul ferrite is
Yeah.
hanging out.
Yeah.
And it's like it reaches its maximum right at that point of 0.02% about.
Yeah.
So if we go, so recognize that that's what we're talking about on that slide. Then go on to the next slide after that, which is also about ferrite. It's an interstitial, like this is the reason why it doesn't behave exactly the same as a BCC structure when we're talking about a pure crystalline structure. It is actually a substitutional phase of carbon
Right.
in an iron structure.
Yeah. So carbon is injected into this BCC formation.
Yeah, and it's the guy in the middle.
Yeah.
So here we've got a few more numbers here. You can look at different things that are happening at 768 on that graph. You can look at what, there's also a different form called delta ferrite that happens at much higher temperatures. And this is something that is a BCC structure that happens about 1495 C. And it basically is the high temperature manifestation of the same alpha ferrite.
Yeah.
Just to keep that in mind. So if we could relate that back to the graph, you're going to see that there is that delta ferrite over there on the, you have to go, because this doesn't go up to that high of
Yeah.
a temperature. If you
You
go
have to
over
go
here,
up on the left-hand side.
you're going to see the delta ferrite there pointed to that other perieutectic
Region here. So
region right
here.
there.
So we're looking at this small triangle. This also has its own diagrams that blow this area up, because
Yeah.
there's a lot of interactions that happen like right at this point.
because it's just below the melt point at
this is
those
just-
low carbon
yeah.
areas.
So, and there's a lot of things that we like to do here from a material properties perspective. We're forming different alloys that becomes
Well,
important.
if you think about it, like in order to form these alloys in the first point, we
Yeah.
have to melt it, and so it's really just about controlling the mixtures and how it cools, right?
Yeah,
and
exactly.
what rate it cools. And so you kind of see, like, if we cooled it down fast from that high of a temperature,
Yeah.
we're going to get different phases than we would if we were doing that same cooling it down from where
Or
it is
same
able
temperature
to
range and letting it cool down gradually.
and go through this eutectoid region.
Right. Exactly.
So, because we get different things if we freeze it at that high temperature phase.
Yeah.
So if we go on to the next slide, perlite is actually a mixture. It's a mixture of ferrite, which we've already covered, and cementite we'll cover later.
Yeah.
But it forms a laminar sort of just a layer cake structure.
Yeah. And so like this is two different phases of iron, essentially, that are sandwiched on top of each other.
And they're kind of ordered.
Yeah.
And
they
they're
have
like-
a directionality.
They
to
have a
them.
directionality to them, so they're a little like, but like they're like a macro crystalline structure almost, because
Yeah.
they're forming these layers, but they're layers of different crystals.
Yeah.
So there you go. This will make a lot more
Yeah.
sense once we cover cementite. So hit the next slide.
Yeah, just real quick, I want to point out one thing where it says coarse here. Like when we're talking about coarse perlite, it's like the distance between these two,
Between the layers, yeah.
between the layers. There's a region in the lower right here that's a finer structure, but this area here is also still perlite.
Yeah, because it's still forming those
It's
lines
like-
there.
Yeah. Okay.
And perlite is so this just to kind of describes these things, so you can go and relate these numbers back to the chart again.
Yeah.
We're not going to go back. You do that on your own time.
Yeah.
Austenite. Austenite is a very tough face-centered cubic, right?
Yeah.
High hardness, high brittlity. You can look at that. I mean, if you just look at that micrograph there,
Yeah.
like that looks more brittle,
Yeah.
right? It doesn't look as soft and squiggly.
Very hard, pronounced structural grain boundaries,
Yeah,
and it looks more crystalline.
it looks more crystalline. Yeah, absolutely. It looks, that just looks harder.
Yeah.
Your gut tells you things that you don't necessarily know, but sometimes it's right. And
Yeah.
that's what's happening here. So you now can relate some of the numbers here back to that graph. Go on to the next slide. Let's look at that, and you can see some of these characteristics here, and relate those back to the graph.
Yeah.
So, and then cementite. And cementite is the hardest structure that appears on the diagram.
Yeah.
And that is because it is its own its own compound. It is a chemical compound. It is ordered necessarily because it is this is actually a covalent bond.
Yeah.
But these molecules, that covalent bond, form a crystalline structure that's orthorhombic, which is really super brittle and very hard. And when we mix the hard and the soft of ferrite
With cementite,
we get this nice little cementite structure, or the perlite structures, right?
Yeah.
Where you have these cementite networks laced back and
Yeah.
forth in between layers of ferrite.
And you can see here, like in these kind of like these valleys looking structures here, we see that reoccurring like layering pattern again of ferrite and cementite happening.
Yeah.
And so like these cementite networks that being pointed at here is a more pronounced continuous form of cementite.
Absolutely.
like,
Absolutely.
yeah.
And, you know, like, the thing is that cementite is usually leaching carbon from other places. That Fe3C, if we look at that, like that's kind of where we go to that, like it's this is the thing that causes that eutectic.
Yeah.
It's the wanting to form this chemical right here, and so like cementite is formed by basically leaching surrounding carbon into it to form this covalent bond structure.
Yeah, and that's why, like at high temperatures, in the example that Jason was talking about with the furnace and the crucible that you were using, this reaction, like if you're not anticipating it, it happens very quickly. Like the thing that we need to remember is that like once the conditions are met for certain types of these chemical reactions, because that's essentially what's happening
Yeah.
there. They will happen and propagate very quickly as long as there's material available for them to occur, right? So
Yeah.
these phase changes and these different states of iron that we're looking at, once you meet those characteristics, they happen.
Bam. So go on to the next slide
Yeah.
here. Here's more information about it, and this is again more data that you would want to relate back to that phase diagram as you're reading through this stuff. So this kind of divides it up, like the eutectoid steels and their properties. Again, relate that to what's on there. Hypereutectoid, which is something that is just to the right
Yeah.
of that on the phase diagram, and what those relate to on there. So again, relate these back to those steel making things. Hit the next slide. And that's really what we've got to talk about. Like the important thing for you to digest this information is kind of more of a reading and relating thing.
Yeah.
It's like actively flipping back and forth between those 10 or so slides
Yeah.
to kind of make sure that you understand like how it relates to the phase diagram and so on and so forth.
Yeah. So I think that wraps it for this section here.
And spoiler alert, aluminum is what we're talking about next.
Yeah.
So we'll see you in the next video.
Sounds good, guys.